All right, so maybe some more people will come. All right, so today we're just gonna finish up our lecture for control systems. Hopefully it's not too long. And so yeah, we're gonna do that. There's not gonna be any coding today. We're gonna do that all next class. I say coding, but there's not much coding for this lab at all. It's mostly Simulink. So we're gonna do that, and let's do that. And yeah, so first off, I'm gonna go over some of the deliverables for lab 2 because I had some questions on that. All right. Okay. So now I'm sharing my main computer. Okay. Turn that off. All right. So I added a new document for the deliverables for lab 2. I did that for lab 1. So I think that just makes it a bit more clear. So lab 1, you can either go in the weeks here or, so if I click on submarine towing experiment, I should see. Oh, that's nice. I think I changed the name. So if you guys were trying to access that before and you couldn't, I need to update that link. So I'll fix that. So if you clicked on the week for the submarine towing experiment before, you could see the deliverables right there. And of course, this is for lab 1. But a different way you can do it, let me go to student view. All right, so a different way that you can access basically just files in the class is go in the left-hand sidebar, click on files, and then I have them broken up by the lab as well. So I'm going to click on lab 3, and I updated the slides for the slides today. And then we have the handout here. Oh, okay, I guess I didn't upload the deliverables under there. I got to do that. Oh yeah, I'm looking at lab 3, that's why. So, okay, I need to put the deliverables for lab 2 under this folder, but here we go. Deliverables for lab 2, you can click on that there, or like I was showing you earlier, let's go home. Let's go to weeks 5 and 6. And then I have the deliverables right here. Okay, so again, I had some questions on that, so I decided just to make a document. So it's just very clear on what I expect to see for lab 2. Okay, so the deliverable is what we need to have, and this kind of includes the sample calcs that you should have as well. I don't explicitly state sample calculations, but they're basically in here. So deliverables, this is all that we did last class. And again, that the lab is due, is pushed back to next Tuesday. So I'm going to grade your labs hopefully by the end of today, but for sure by the end of tomorrow. So yeah. So deliverables for lab 2, we have the theoretical natural frequency for a simply supported beam. That's just going to be one value. We solved for that in MATLAB. And number 2, we have the experimental, and this is going to be for all of the intervals of mass that we added. We have the natural frequency from LabVIEW and from the strobe gun. So we recorded that directly with LabVIEW or the strobe gun. We had to do a little conversion to change it to rad per second, but again, that's in MATLAB. Of course, all of this stuff here we solved in MATLAB last class or 2 classes ago. All right, so we have that, and then you're going to also include the percent error for those readings. So the percent error for LabVIEW and the percent error and for the strobe gun. And then you're going to have the effective stiffness and the effective mass. Oh, that's cool. I didn't notice my highlighting changed to purple for some theme. Okay, so effective stiffness and effective mass. And you're also going to show the percent error for both of those compared to the theory. And we calculated that again in the code. And then we have the theoretical calculations for all added mass intervals once again. So we have the natural frequency for the system and the effective stiffness and effective mass. All right, then we have our least squares plot. So that was 1 divided by our natural frequency, and this is what we recorded experimentally, either with LabVIEW or the strobe gun, and we plotted that against our added mass. So that's these plots right here. So these two plots, or two figures, I should say, they're basically the same thing, right? So in this top part here, I have a subplot. I'm going to make this a little bigger. Okay, so here I have a subplot. And so on the left here, we have the LabVIEW readings that we had. And on the right, we have the strobe gun readings, and we did a least squared fit to it. And then down here, those are the same plots basically, but now they're overlaid. So I want to see both of these plots, or both of these figures. All right, so that's the plot right there, and I specify both of those figures that I want to see. And then we have a question here: is the strobe gun or acquisition with LabVIEW more accurate to find the natural frequency? So you'll talk about this and mostly in your discussion, this question right here, and sources of error. You're going to go over that in your discussion as well. Okay, so for lab 2, again, I'm going to hopefully have that done by the end of today, but for sure by the end of tomorrow. Or sorry, lab 1. Keep kind of mixing them up. So I'm going to have your grades for lab 1 due by the end of today or tomorrow. So you can look at all my feedback that I'm going to have, and you can incorporate that for lab 2, which is due next Tuesday. All right, do we have any questions on lab 2? Okay. All right, so we're gonna get started then. Also, is there any question on the formatting for the labs? Okay, so the formatting, that should be pretty clear too in the syllabus. I kind of have the structure laid out there, so let me quickly go over it. But we talked about this before. So this is the formatting for the memo. So we have the abstract, results, all the sections that we have in the memo, and then what I expect to see in it. So some of you didn't have references for lab 1, and I think, I already graded all of that part for all of your memos, and I think I gave you 0 points for that, but I think I'm going to actually change that just to be a little forgiving for the first lab, but you'll see that once I actually upload the grades.
Hey, Patrick, I had a question about that.
Okay.
So using your template, the LaTeX template, is there any way after class maybe you can show how to add references using that template you have there?
Yeah, I can help you with that. That's kind of a weird thing, I know.
Yeah, thank you.
Okay. All right. Any other questions? All right. So now I'm going to stop sharing this screen. I'll share the other. All right. Okay, so we're going to finish up what we talked about last time. So that's our control system tuning slides. Okay, so I'm going to just go through what we had. Yeah, okay, this is kind of still an awkward setup. Okay, so last time we talked about control system tuning, kind of the first part. And now we're going to finish up what we had last time. So today, we're mostly going to focus on a closed loop system. And we'll talk about our controllers that we're going to have for the experiment. So our controllers, they're going to read the error. That's, the error is calculated from the difference from our input and our actual output. And our controllers are going to act on that. Sorry, my laptop again is extremely loud. I hate the fans. So the controllers, they're going to act on our error, and they're going to kind of adjust for the error to make the system respond more like we want it to respond, right? More closely to what input that we have. Okay. So I'm scrolling with my left hand here on my laptop. It's weird. So we talked about transfer functions last time. That's going to relate some output that we have to the input in an algebraic kind of equation. So we had some review on that last class. We had some funnel applause review. We had, I think, 2 examples. So I'm just going to skip through this. This will be important right here. So let's see, right here, we had a transfer function that was relating our position and our input force. So this transfer function right here, we were using that later on for our closed system kind of formulation. So this transfer function, we later call it g sub s. And again, that's relating our input force to our output position. So we're going to use this transfer function inside of our system for a closed loop. So just keep that in mind. This transfer function is going to be called g sub s. All right, let's keep going. I'm just kind of looking at each slide to see if there's anything that we should kind of refresh our minds on. Okay, so a closed feedback loop, we already talked about that. That's going to act on the error that we have and make adjustments to decrease the error. Compare that to an open system. We're just going to have some input and we're going to have some output. And we're going to cry when the output is bad because we can't change anything. We don't have any controllers. All right, so here's our closed loop feedback system, well, one model. So here is g sub s, that's the transfer function that I just talked about, that's relating our input force to our output position. And here, h of s, that's kind of our monitor to see our output that we have. Our output in this case is a big Y sub s in the Laplace domain. And then that's going to go back, and then it's going to go right here. So our error, that's looking at our input minus our output, and then our error is calculated. And then it goes to our controller here. In this case, it's called a proportional controller. And that's just going to apply some gain, some proportional gain to the system to try to make it better. So we'll talk about different types of controllers in this lecture. So there's a proportional controller, which is what we have here. And there's a proportional derivative controller. And we have and that's a PD controller. And then we have a PID controller, which is proportional integral derivative. In this lab, we're actually just going to use a proportional derivative controller. So not a PID controller. A PID controller would be more accurate, basically, but not by too much for what we're doing. So we're just going to have a PD controller. All right, then we had our equivalent open loop system that we solved for. And then we talked about the importance of our Kp value, which is our proportional gain value again. All right, and then we saw that we had to choose a very large value for our Kp right here, based on what we needed to have, which is our particular solution. It had to be equal to 1. All right, so that's all that we covered last time. So now we're going to start right here. I'm not going to write everything down on the slides just because, some of this stuff gets kind of tedious, all this math here. I'm not going to write all of that down. I'll kind of write the important stuff. And if you want to look at all the algebra, which I doubt, but if you do, you can look back on the slides. So I just want to make sure that I cover the important topics and write down what I think is important, just so we don't take an extremely long time. Okay, geez, I keep saying it, but the fans on my laptop, they're pissing me off, man. Way too loud. Okay, so let's get started now. Let me move my mic down. Okay, so let's get started on the iPad. No, I've never done that, Adrian. I didn't even know people did that for MacBook. I mean, I clean my PC a lot, but I've never cleaned out the MacBook. Maybe a good idea. Although, don't they have like proprietary screws? Yeah, I'll see if I can actually open it up or not. Okay, I don't know if it's just for new Macs, but they have proprietary screws for some stuff, or maybe that's just for their phones. Anyways, I'm gonna take a look at that. All right, so the date, what is it? It's the 13th. All right, so right now we're going to talk about the effect of noise on our system. All right, I'm just going to make the slides a bit bigger. So you can't even really see it because it's in white here, but this says, I need to actually look at my laptop. Yeah, okay, noise on a closed loop system. So that's the section that we're in. And this is the closed loop system that we have right here. So we have our input, use of S, and then we have our, this is our gain here, which is just looking at our output. And then we're going to compute the error right here. So that's just our output our input minus the output. And we're using just a gain of 1 here, just so we can directly look at the output that we have. So calculate the error. And then after that, we use our proportional gain controller right here to act on the error and try to improve the system. So right now we are adding this this kind of, force right here called TD. And TD, that's going to be some noise on the system. So for our lab, that's going to be our bird. We have an eagle and we have a hawk that smack into an airplane and they cause a disturbance on the system. So that's going to be big T of D. Okay, so that's our noise that we have. And then we're going to apply a transfer function. In this case, it's G sub S, which, if you remember, that was our relationship for the input force to our output position. All right, so that's what we have right here. So now we're going to take a look at our output. So our output is Y sub S, and that's going to be equal to our transfer function G sub S multiplied by kind of an effective transfer function here, TD, which is our noise, plus KP times E sub S. So KP, that's the proportional gain once again, multiplied by E sub S, that's our error. All right, so let's write this down. I should have copied and pasted this figure in my notes here. I can do it right here. I kind of hate drawing stuff out on my iPad, so when I can copy and paste stuff, I'm going to do it. All right, so we have this, and I do need to add one thing here. Okay, so we're going to have a summation block, which is going to cover our inputted noise to the system. I think I saw in some of the lab reports that you guys had that some of you also use, at least it looks like you use Notability. Great app, great app. Okay, so there we go. So that's going to be our system right now, and I guess I can modify h of s to be 1. That's going to be our constant gain for the output that we have. Okay, so we're going to look at the output. And again, what we're doing right now is we're trying to look at the effect of noise on the system. So I guess I should actually write that out here. So if you look back at your notes, you can know what we're doing. Okay, so let's look at the output. So we're going to have big Y sub s equals our transfer function g sub s, that's relating the input force to our output, multiplied by the noise that we have on the system. That's the bird just going ham, plus kp, our proportional gain, multiplied by the error, E sub s. Okay, so I was scrolling on the wrong computer. So recall from last time, E sub s, that's the error, that's going to be our input minus our output. So we're going to plug that back into the equation that we just wrote here. So we're going to have G sub s multiplied by the noise of the system plus Kp, and then multiplied, we're plugging in right now for the error. So that's the input minus the output. Okay, so there we go. And now what we're going to do is group like terms. So we're going to get basically Y sub s on one side. So we have we're going to do that, and then also we're going to basically group G sub s and U sub s as well. So basically we just want to rearrange this where I can have Y sub s on one side and then U sub s on the other side, so we can develop a transfer function, which later we're going to basically convert that, take the inverse Laplace, so we can get an equation of motion right here where we can solve for the output of our system. Okay, so I'm not going to write out everything for grouping terms just because, again, I don't want to write down kind of needless stuff, but I'll write out that step, but not actually all the numbers. So we're going to group terms. And then we're going to get Y sub s times 1 plus Kp G sub s equals G sub s Td of s plus Kp U sub s. I know my handwriting isn't great, so that's why we have the slides though. And then we're going to plug in for G sub s. So G sub s, we talked about that a few times now. That's our transfer function, which was relating the input force to the output. Okay, yeah, at first I saw this and I was a little confused myself, but we have 1 plus Kp times G sub s. So G sub s, that was 1 divided by ms squared plus cs plus k, and since we're multiplying it by our proportional gain, we have Kp divided by ms squared plus cs plus k. So plugging in for G sub s, then we're going to get Y sub s times ms squared plus cs plus k plus kp equals td of s plus kp u times s. All right, so now we want to get an expression here for the kind of an equation of motion, right? For the output that we have, which is y. And then in this case, if we solve for it, we'd be solving for the position. So we're going to take the inverse Laplace here. So we can go into the time domain. And then we're going to get m y double dot of t plus c times y dot of t plus k plus kp multiplied by yt equals td of t plus kp u sub t. All right, so y sub t, that's the output. K, that's the kind of the stiffness of the system. Kp, that's the proportional gain. Td, that's the noise on the system or the bird. And u sub t, that is our input. Okay, so I think we wrote all of that down last time, so I'm not going to write that down. Okay, so now we're going to, kind of further take a look at the effective noise on the system. So we're going to kind of make some, not assumptions, but we're going to state some of our kind of problem knowns here. So let's say that the input of the system, u sub t, is going to be equal to 0. Okay, and then we're going to say that the noise, let's say noise td of t, that equals 1 for a time greater than 0. And we're going to kind of model this as a unit step function. So it's going to be 0, and then at time greater than 0, we're going to have a step function, so it's going to go up to 1. All right, for t greater than 0. So that's kind of, it's going to be like basically an impact, if we think about it that way, where, we're just kind of flying, we're chilling out, then all of a sudden we have a bird that just broke the windshield on the plane, and we got to land. Okay, so if we kind of think about this right now, our input is 0, and then, we want our output to also be 0 then. So our input, we can think of that for our lab, it's going to be the roll angle that we have. So if we aren't, rolling the plane, then we want that to stay at 0. So we want our output, obviously, to also be a roll angle of 0. We're going to have some noise on the system, so a bird is going to strike the airplane. And in this case, we're modeling that as a step function of 1. And that's going to obviously have an impact on the response of the system. Well, we want our output to equal the input, so we want the output to be equal to 0. So we're going to need to do some things with our proportional gain for that controller to make sure that we can get as close to 0 as possible. Okay, so now we're going to plug in for our input, which was 0, and our noise, which was 1. So I'm going to call this equation 1 right there in purple. And then we'll do plugging into equation 1. We're now going to get, wow, great m double dot of t, y double dot of t, plus c y dot of t, plus k sub p times y sub t. And now that's equal to 1. So it's just equal to 1 because our input is 0, and then our noise TD, that's equal to 1. All right. So kind of like we did last time, we're going to assume that the homogeneous solution is going to disappear. And then all we're left with is our particular solution. And then, so what we have to do now is solve for the particular solution. And our goal is to have that particular solution match our input, which was 0, which is going to eliminate the effective noise on our system, which we said was 1. And again, that's due to a bird striking the airplane. All right, so let's write a little note to ourselves. Actually, we need to specify our assumption. So assume homogeneous solution disappears 1s. Okay, and we're left with the particular solution. Okay. So now we're going to solve for the particular solution. So solve for particular solution. So we have a constant of 1, right, on the right-hand side. So we're going to use our method of undetermined coefficients, and we're going to solve for y sub p, or y sub p's of t. Okay, so we have y sub p, that's going to be equal to a. It's equal to some, just some constant value, a, or whatever variable you want to use, because our right-hand side was a constant of 1. Okay, so we're going to take the derivative, and that's going to be 0 since it's a constant. And then y double dot of p is also going to be equal to 0. All right, so now we're going to plug our variables, y sub p and y dot of p and y double dot of p. We're going to plug that back into what I just wrote down, equation 2, and then we can solve for a. So plugging into 2. Okay, we're going to have m multiplied by 0 since we have y double dot equals 0, plus c times 0 because y dot is equal to 0, plus k plus kp multiplied by a because y sub p equals a, and that's equal to 1. All right, so let's kind of rearrange our stuff here. So we have a is then going to be equal to 1 over k plus kp. Again, the difference between the two, k is the kind of the stiffness of our system, and kp, that is the proportional gain for our controller. Okay, so now we're going to plug back in. Now that we solved for a, we're going to plug back into our ODE and to kind of solve for y sub p. Okay, so we're going to be plugging back in to the ODE right here. And then we're going to solve for y sub p. So plugging back in. Okay, so we have y sub p equals a, which is going to be equal to 1 divided by k plus kp. All right, so that's going to be our output position that we have for our system. And now let's think about, again, reducing the noise. So let's actually box this. Okay, so recall we want to have our output y sub p equal to 0 because our input was 0. And we had noise on the system, which was 1, so we got to deal with that in some way. Okay. So if we look at our equation here, we have y sub p equals a, which is equal to 1 divided by k plus kp. So if we want this to equal to 0, we're going to need to have a very, very large value for kp, which is our proportional gain. Okay, so to do that, we're going to have to take the limit as kp approaches infinity, and then we'll have y sub p equal to 0. All right, so there we go. So we have for noise TD equal to 1, the proportional gain of our system. It must approach infinity to reduce the noise of our system to match the input, which was 0. So this example, it's going to be, an extreme case because our input was 0. So but this is just kind of course, to show the effective noise on our system. All right. So do we have any questions on that? Okay. I just moved there we go. I moved my window. Okay. Get my chat. Okay, so now we're going to talk about PD controller. So really this is, I think, more the main focus for this lecture. So, the math is important, of course, but, we did a lot of the math last time, and this time we're mostly going to talk about the differences for controllers that we have for a system, a closed loop system. So far we've only introduced a proportional controller. All right, there we go. So far we only had a proportional controller, which was KP, and again that was to just adjust our error to kind of reduce the error of our system to better match our input. Okay, so if we added a derivative controller or a D controller, that's basically going to be where we multiply a derivative gain on the system. So that's going to be KD, that's going to be the kind of variable that we have. And that will be the derivative of our error. So that's going to be just the derivative of the error. So that's a function of time. And we're going to take that derivative like I just said. So we can combine both of those controllers. If we can combine a proportional controller with a derivative controller, we're going to have a proportional derivative controller or a PD controller. So in this case, we're going to get rid of the mouse. We're going to be able to get to our desired response faster and smoother than if we just had one controller. So think about it. If we had a proportional controller that's only multiplying some gain or dividing by some gain value, so that it's not really a great way to adjust for the error of our system. So we'll actually see this visually next class once we go into Simulink, because I know still right now it's kind of abstract to think about it. But if we multiply by the derivative of our error as, again, a function of time, then we can better adjust the error of our system to kind of go to our input, our desired input faster and smoother than if we just had our proportional controller. Okay, so what we can do if we combine those, what we're effectively doing is adding stiffness that's with our proportional gain. So that's just Kp, so that's some constant that we're multiplying or dividing by. Or we can add damping. well, you can kind of think of it like damping, which will be our derivative controller case of D. And that'll help us have a smoother and a faster response trying to get to that input that we prescribed for the system. All right, so let's write some of that down. I'm not going to write down all of it. I think this is kind of better just to look at these slides here. But of course, if you want to look back at your notes, we should write some of this stuff down. Okay, so we'll say add a derivative controller. So add a derivative D controller to the system. And then below that, we'll put a smoother and faster response to approach desired output. Okay. And then we'll write down what a derivative controller actually is. So that's multiplying our, in quotes, our derivative gain, which is the derivative of our error. All right. Okay, there we go. Guess that's what we have. So to better have an output that is equal to our input, we're going to add on a derivative controller to our system. Okay, and this is what it's going to look like. So before we kind of had the system here. So let's actually go up in our slides. Okay, so I'm going to resize that. So we kind of had a system that's very similar to what we have in the slides here. So all we've done, if we compare our system on the left to the system on the right, is we've added a derivative controller right here. So it's kind of small, but in this box here, it says KP plus KD times S. So KD, that's our derivative controller, and we're multiplying it by S, because if you remember, that's the transfer function for a derivative. So we have S here because S is taking the derivative of our error here, which is with respect to time. So in this case, we have our error, we're multiplying it by our proportional gain, which is Kp, and we're also implementing our derivative controller, which is Kd, and we have multiplied by S because that's taking the derivative of the error with respect to time. All right, so what I'll do is I'll go in the notes. I'm gonna, of course, again, copy and paste this so I don't have to write too much. So here we go, and then we're just going to adjust the box that we have. Okay, so we have KP plus KD. Maybe I should I'll write it like that. So KD times S. So again, S, that's the derivative of the error. All right, there we go. So in the slides here, it shows h of s instead of 1, but remember we're using a constant gain of 1 because this is basically a sensor for our output. We don't want to modify what we're reading for the output, so we use a gain of 1. Okay, any questions on the PD controller? Okay. So now we're going to kind of think about, what we just talked about and kind of apply some context to our experiment. So this will be, I guess, a little bit of a refresher too from last time if I talked about it. So our experiment, we're going to simulate an airplane to fly with a desired output. So we want our output to match our input. And for some scenarios, we're going to have to overcome external disturbance or the bird strike on the airplane to return to equilibrium. Okay, so we're going to have two different setups. We're going to have an open loop system and a closed loop system. And just of note, this experiment, it's simulating the performance of an airline control system. I think I said that wrong. Aileron, I can never say. I think aileron. Control system for an aircraft rolling motion. Okay, so for the open loop, this is what we're going to be doing for the lab. We're first going to have a kind of a scenario with no disturbance. So we're just going to be flying. And we're going to give an input roll angle of 1 degrees. And we're going to view the response. I guess I should have said 1 degree. And then in our next scenario, we're going to have a disturbance. So we're going to have an eagle strike the airplane. And we have an input roll angle of 0 degrees. And then we're going to view the response. So we're going to be flying. We have an input of 0 degrees, so we're just going straight. We're not turning at all, or there's no roll. And then an eagle is going to strike the plane. So we need to see if our response is going to be able to handle that disturbance and go back to equilibrium or not. So for the open loop system, I think we're only using, we're not using any controllers because we need a closed loop system if we have a controller. So what do you think is going to happen? It's not going to work out too well. All right, and then we're going to have our closed loop system here. So we're first going to start out with just a proportional controller. Move my mic up. There we go. So we have first a proportional controller, and we're going to have, for one scenario, an input angle of 1 degree, and we're going to view the response. Then we're going to have an input angle of 5 degrees and view the response. All right, so we're going to do that. And then we're going to implement a PD controller. So we're going to add in our derivative gain, and we're going to have an input angle of 5 degrees, view the response. And then we're going to have an input angle of 0 degrees, have a hawk strike the plane, and then view the response. So what we should see here is, right, so for our open loop, we have a bird strike, right? And we're going to view that response. So it's not going to be good. It's not going to be stable. And down here for the closed loop, we're going to have a hawk strike the plane. And it's going to be at a larger force or a larger impact force than the eagle up here. But we'll see that in our closed loop system here, because we have controllers, it'll be able to handle that disturbance and go back to equilibrium. All right, so any questions on the setup for the lab? Of course, we're going to do it, next time, but any questions? All right. So this is, I guess, a better kind of way to show what we're doing inside of Simulink. This is the model that we're going to have. So we're going to have our pilot action, or that's our desired input. And then we have our error here, which of course we're reading the error because That's going to be our output that we're looking at. We have our sensor here, which is just going to be a gain of 1. That's going back here to then have the input subtracted by the output to give us the error. So now we have this error value, and then we have our controllers here to read the error, evaluate it, and decide what we have to do to fix it. So we have our proportional controller right here, that's KP, and then we have our derivative controller right here, which is KD. So those are they're gonna do some things. We're gonna specify what they have to do based off of the Ziegler-Nichols rules, and so we're gonna apply some stuff here. And then we're going to have our actuator, which will implement those changes in our system. And then we have our airplane dynamics, which will be our transfer function. And then that'll go to our output. All right, so that's kind of the plan. Okay, so we have a PID controller. So I have this slide, but really we're not going to be implementing a PID controller like I said earlier, but it's good just to know what it is. So a PID controller is going to be a proportional integral derivative controller. So a PID controller is going to evaluate the error of the desired input and the actual output that we have based on proportional, integral, and derivative terms. So our proportional term, again, that's some constant gain value. Our integral term, that's going to obviously involve integration. And then our derivative term, that was evaluating the derivative of our error with respect to time. So here I'm actually going to break it down for each controller. So we've talked about P&E controllers for a bit now, but let's just write down some of the main points here. Oops. My mic is like really close to my speaker, so if you heard a big thump, that was why. Okay, so first we're going to have a P controller. So that's going to be a constant gain value. We've said that, I don't know, 100 times now. Not really, but you know. So our error is going to be multiplied by some proportional constant to modify the output. When I say multiplied by a constant, you know, we're either going to have, you know, some whole integer like 2 or something, or we can do basically 1/2. So we're essentially dividing in that case. Okay, so we'll say the error is multiplied by a constant, by a proportional constant. To modify the output. Okay, and then the big takeaways here are that we can have a stable operation. That'll be very hard to do, but the steady state error is going to be maintained. So we're never going to actually reach our desired input. We're always going to have some error. So even once you reach steady state, there's going to be some error that we just can never reach because we're only using a P controller. So once we do the lab, we'll be able to see this more visually because we're going to be adjusting values throughout, and then we'll see that as we adjust our proportional controller, that we can start to approach that input that we want to have, but we'll never actually be able to reach it with just a P controller. And you know, I keep going like this if my webcam shows it, because we're going to kind of approach it, but we're never actually going to get there. All right, and then we have our speed of the response is increased when our proportional constant Kp is increased. So let's first write that, and then we'll talk about it. All right, so I don't have this part in the slides, but it'll be good to kind of get an idea of what I'm talking about here. So we just wrote our speed of the response is going to be increased when our proportional gain value Kp is increased. So here in pink, all right, I can't make the my notes any bigger for the window, but there we go. So in pink here is our input that we have for the system. So let's see that this is going to be theta. Okay, so theta I, that's the input. That's basically the roll angle that we have. So I want to reach that input. Let's say it's like, I don't know, 5 degrees. Okay, so we want to reach that input. If we have a proportional gain controller, now it might not actually exactly look like this, right? But it'll again just be kind of to demonstrate what we're doing here. So if I have a proportional gain of some value, it doesn't matter. So maybe it looks something like this, okay? So we'll say Kp equals 2. Now, it might not be 2. That part is kind of irrelevant. So we have Kp equal to 2. So we see in the beginning, our output angle is terrible. Obviously, it's 0. We want that to match our input. And also here on the x-axis is time. Okay, so with Kp of 2, it starts out terrible at time equal to 0. And then as time goes on, we start to approach our input angle of 5, but we never quite get there. So maybe that's 3 degrees. But as time goes on, we get closer and closer. But because we have just a proportional gain controller, which is Kp, we're always going to have steady state error, which is that error right there. Okay, so with our Kp controller, we see that our angle or the output, it's gonna kind of, it's gonna plateau out at 3 degrees. So no matter what, even if we go on and on and on in time, we're never gonna reach that desired output angle of 5 degrees. So if I increase my proportional gain controller, what we'll basically see in the end is we're going to go something like this. Again, it might not be drawn perfectly, but it's just to kind of demonstrate what we have. So actually I should draw a little different. We'll do it like that. Sure. No, still don't like it. Like that. Sure. Okay, there we go. So we're going to say that this is a KP equal to, I don't know, let's say 7. Again, it doesn't really matter, but we increased KP to some value. Right? So here, I still don't like the graph here. I need to draw it again. Hopefully you're not drawing it on paper really fast and you keep erasing right now. All right, that's better. So there we go. So we have KP equal to 7. So here, you'll see that the response here, it was increased. So it's going up really fast here in our kind of beginning portion here. It's going up really fast with not a lot of time. And then we reach our kind of steady state value kind of right here. So it reaches our steady state value before KP equal to 2. But again, we're always going to have some steady state error. Now, how I drew it here, that steady state error looks pretty reasonable, right? But it might be really, in reality, greater than that. Right, so we have our steady state error, and so we're not going to actually really get to 5 degrees. And you'll see that we got to our steady state value faster here than, or we got to our steady state value with KP equal to 7 faster than we did with KP equals to 2. So that part is good, but we have an issue here where we have very large error in the beginning here. So here if we have what's called overshoot. So we really overshot our desired input angle of 5 degrees. So that's going to be an issue, right? If we have this controller here. So that's why we're going to then implement a D controller as well. So we're going to have a PD controller to better manage our overshoot, to kind of bring that down and to also get closer to our steady state error or our steady state response so we can decrease that steady state error. Now, I think I mentioned before that we're never actually going to totally achieve our desired input or output with a PD controller. So for that, we would need a PID controller, but we're not using that for this lab. Okay, so we'll just put in blue here. All right, so we need to use a PD controller for a better response. Okay, any questions on this part? Okay. All right, so now we have our D controller. So our D controller is it's going to try to anticipate the future behavior of error. So once we kind of loop through our system, this controller is going to be able to kind of take an estimate of what the error is going to be, and then it can kind of take that into account to then modify our system to decrease the actual error. Okay, so we have the output is dependent on rate of change of error with respect of time. We discussed that. And it's multiplied by our derivative constant s. That's our transfer function s. That's to take the derivative of the error. All right, and because we are anticipating error, it's going to directly improve the output of the response and then increase our system response. So it's anticipating the error, so it's basically going to be able to implement a change to our system right away, and it's gonna make that change, and then it's going to apply it right away, and then we're gonna have our output. So it doesn't have to loop too much to already start to apply a change to the system. It's able to implement, kind of think of it like it's able to implement the change on the fly. All right, so we'll write some of the stuff down. So D controller. With these slides, they might be good to look back at once you actually start to write your memo. To kind of talk about stuff in your discussion. All right, so it's going to improve our system response and our stability. So let's think back to our little figure that we drew here for just a KP controller, just a proportional controller. So when we used a KP value of 7, we had a very unstable system at this earlier time right here. That was pretty unstable there. It started to be more stable towards the end. Really, I still probably drew it at too kind of idealistic. It really wouldn't look this good for the steady state area that we have in purple. But whatever, I'm not going to draw it again. So if we implemented a D controller as well, it'd be able to reduce that big instability right here, and it would also improve or decrease the steady state error that we have for the output. Right, and then we have our I controller. So our I controller, that's going to be the integral controller that we have in the system, and that's going to try to eliminate the steady state error. So if we use an I controller, that's going to, in theory, take out all or just about approach, having zero steady state error in the system. Right, so this is going to integrate over a period of time, or it's going to integrate the error over a period of time until the error value reaches 0. And once we get there, it's going to hold that value. And because it's holding that value, it's going to make sure that as we are in steady state, it's going to keep that steady state error at 0. All right, there we go. So I just wrote down everything that we just discussed. All right. All right, so now we have our Ziegler-Nichols rules, if I said their name right. So Ziegler-Nichols, this is a method to tune a PID controller. So we're just using a PD controller, so it's kind of adjusted to what we're doing in the experiment. But you'll see this if you're using a PID controller for whatever. This method is going to be used quite a lot. So it's kind of a systematic way to optimize our controller to reduce our steady state error in our system and to have a stable output. Okay, so basically what you have to do so let's just imagine that we're using a PID controller here. We're going to set our integral, so our I term, and our derivative, our D term, to 0. So basically from the get-go, they're not doing anything. While they're in the system, we're going to basically turn them off. Then we're going to take our proportional controller, our proportional gain controller, and we're going to also start that at 0, technically. And then we're going to start to systematically increase this value, this KP value, until what we have is called an ultimate gain, or K star, is achieved. So K star is going to be when our system is marginally stable. So it's not stable, but it's marginally stable. Right? And then once we get to K star, then you start to also basically tune your derivative controller and your integral controller based off of a formula. So the formula, I guess, I don't know if I wrote it in here. Yeah, right here. So you'll see once we get to K star, which is our ultimate gain, then we're going to also then change our proportional gain again based off of that value that we just had. So our proportional controller is going to be equal to 0.45 times K star. Again, that was the ultimate gain. And then our derivative controller, KD, that's going to be equal to 0.125 times KP, and times T, that's going to be the period. So I kind of skipped ahead here, so we'll go back. Okay, so that's kind of the method that you would use to tune your controller. So we're not using an integral controller, like I said, but this is still kind of the method that we're going to be using. So we're first going to start off with our proportional controller only, and we're going to start to kind of iteratively increase that value until we reach a marginally stable system. And then we're going to change both the proportional controller and the derivative controller to some value based off of equations to then have an optimized system response, or response for the system. Okay, yeah, I don't think we need to write that part down. It's just a kind of theory that you can think about in your head. Yeah, I feel like we should write it down, actually. I was trying to convince myself. All right, it's not too much, though, so. Ziegler, I think I spelled Ziegler wrong last time as well. Don't blame me. Well, you should blame me, but it's based off of some slides I was looking at, but it's Z-I-E, not Z-E-I. Okay, so this is a method to tune a PID controller. So I'm going to put 1 I on D equal to 0. So that's our integral and derivative controller. Both of them are equal to 0. 1.1 ... Sure. Adjust KP until marginally stable. And that equals K star. So I know I wrote K star a little different now. Same thing though. And then we're going to adjust K star, not K star, KP, right? Yeah, KP. All right, so adjust KP and KD with equations. Yay, we got equations. Makes it a bit easier for us. All right, and then I have a note that since we're using a PD controller, we're going to have some steady state error. All right, so what's the plan, man? This is going to be the plan for the experiment. The mic again. So no, before we do that, let's write down those equations so we don't need to write anything more today. Okay, those are our equations. We have Kp, that's going to be equal to 0.45 K star. K star, that's the ultimate gain. That's when our system was marginally stable with just a proportional controller. And Kd, that's going to be equal to Kd, the derivative controller. That'll be equal to 0.125 times Kp, what we just had, multiplied by t, which is going to be our time period. All right, get out of there. Don't need to write anything anymore. You know what? Because I'm tired of hearing my fans. Hopefully they kind of shut up now. I'm going to share my screen on my other computer. All right, here we go. All right, so what's the plan, man? I don't know. This is going to be for our experiment, right? So we're going to talk about it, of course, in more depth next class. All right, so this is what we're going to do. This is when we're getting our marginally stable system. So we start out with our P controller, or just our proportional controller. And we're going to adjust Kp, so that proportional gain value, until our system is marginally stable. All right, so this is what a marginally stable system looks like. We have some oscillations here, but our oscillations, they stay the same. So even though it's marginally stable, it's never going to reach equilibrium. All right, and then this kind of graph here, this is a graph that's inside of Simulink. So this is what you're looking at. And this kind of reminds me for lab 1, a few of you who shall remain unnamed, you didn't, what I say in quotes, fully save your figure. So actually, before we end today, I'm going to go over how to fully save your figure. I can't remember if I docked you a point or not. I don't think I did unless you had a few other kind of formatting issues. But I hate, well, maybe I shouldn't say hate, but I don't like seeing it when it's not fully saved. So I'll show you what I mean. All right, so we have our, it's kind of a tangent, but so we're going to adjust Kp until it's marginally stable like this. Oh, there's something in the chat. All right, so, well, that's like a story. I know PID controllers are used for tuning suspension systems in cars, but I gotten really used to dealing with this when building quadcopters. It's extremely important to tune your PID so your quad can handle oscillations from imbalance, prop, wash, and wind. Just the more you know. So what do you mean by, well, no, that's interesting though. So what do you mean by .avs file? I don't even know what that is. Oh, so we're gonna save them basically by exporting the graph, and I don't even know what a .avs file is, but we're gonna save it as either a vector or a PNG. So I'll show that though. Okay. All right, so we're gonna reach this marginally stable kind of I don't know, spot here. My fans they stopped now. It's great. Okay, and then once we do that, we're going to measure the time period here. So we're going to look peak to peak. Okay, and that's going to give us our time period. So in this case, you'll see in the experiment, we're going to have a time period of 21.8 seconds. So it might be kind of small, but there's these little circles here, and we can click and drag them ourselves to go up to the peak. And on the right-hand side here, we can actually look at our values here and the corresponding time. So you're going to adjust these circles until your value is a maximum at each of these peaks. Okay, just looking at the chat. All right, so we discussed this part. So this is our time period right there. And K star, again, that was the value of Kp for when we have a marginally stable system. All right, so that's it for the slides, but hold on. We're gonna show you how to fully save a figure in MATLAB. Oh, spoilers, this is for our lab. This is from undergrad. I'm gonna write better code, to be honest. Let's see. All right, so this is from lab 2. I'm just gonna run it. Hopefully I have some figures that are gonna export. Yep. Or show up, I should say. Okay, so some of you, I'm guessing you just go to save as here, and then you can save it as whatever figure. Or you took a screenshot, I'm not sure. Or maybe just press save there. But for some of you, I saw your figures, they looked like this. Yeah, Adrian, I like SVG, so I'm going to talk about that. So some of you, your figures, they looked like this. Maybe it didn't have this top toolbar up here, but it has this kind of gray background, and it just doesn't look that nice. So what you should do is go to File, go to Export Setup, and then once you're here, all right, some of the figures too, and I don't mark you down for this, but some of them, they look really compressed, and it just doesn't look good. So what you're going to do is, let's actually go back. So here we are at our figure. We go to File, Export Setup, and then under Properties, I'm going to click on Rendering, and then I'm going to change my DPI. Instead of Auto, I'm going to put it to 300. 300 is always very good, even if we scale it up a lot, especially if it's a vector. If it's a vector, it's always going to look good. So we can put it as 300 DPI, and then we're going to click on Export. And let's pretend we're saving it right here. So files of type, we're going to change that. So you can either use a .png file or extension, or a .svg. So SVG, that's a scalable vector graphic. So I would recommend this. Now, I think a few of you are using LaTeX, which is great, but when you use LaTeX, it's kind of a pain in the ass to import an SVG into LaTeX. So in that case, you can use a PNG file and it's still going to look good. Yeah, let's actually do this right now. So I'll import this, or I'll export it right here. All right, so this is good. We'll call it SVG. There we go. And then I'll press OK. And then I'm also going to save one as a PNG. We're just going to do this pretty fast here. So we're at 300 DPI. So for some of you, I'll put a comment to increase the DPI. So that's what you're going to do. And again, I don't think I marked anyone down if it was a kind of bad resolution. I'm not like that crazy about it, but I think you should save it as an SVG or PNG if you can. All right, so now we're going to save this one as a PNG. All right, there we go. And then what I'm going to do now is show you what they look like. So you're going to see the difference for an SVG and a PNG. All right, so here's our PNG file. So if I zoom in on here, you still, like, I gotta zoom in a lot, but I see some pixelation there, right? Let's see what's going on in the text. You see it's kind of pixelated. That's just, I have to zoom in quite a lot. So this is good like this. But let's show you an SVG. So my image viewer, it can't open it up. So it opened up Inkscape, which is a program, but if you save it as an SVG, you can directly paste that into Microsoft Word if you're using that. All right, now if I zoom in here on our SVG, look at that beauty. It's just a solid line, no pixelation. It's great. If I go over to the text, look at that. Oh, it's so great. So save it as an SVG if you can, or if you're using LaTeX, you can go through all the pain of getting an SVG in there. In fact, you have to actually use this program, which is Inkscape, to get it to actually import into LaTeX. But to just kind of recap, save it either as a PNG at 300 dpi or an SVG. Okay, so that's it. I know maybe I sound like a boomer or something, like I'm yelling at you to save it as a higher quality image, but this just looks way better than some of the compressed images that I saw. And I want to reiterate, I didn't mark you down for it, but this just looks more professional and it's much better on the eyes to look at. Okay, so that's the little tangent over. So that's all I have for today. So I'll see you guys next Tuesday. We're going to be doing the lab. It's going to be mostly in Simulink. So see you guys then. If you have any questions, you can stick around. Yep. See you guys.